Good afternoon, everybody. My name is Matthias Lorick. I am a electromagnetic simulation specialist here at RANSIM, and today we're going to talk through how to use Ansys electromagnetics tools to achieve successful regulatory compliance in your designs for EMC. So just a brief agenda, kind of going over what we're planning to talk about today. First, I'm going to give an overview of EMC and what it is and how it's relevant to electronics. And then we're going to dive into two tools that are within the Ansys electromagnetics suite that we are going to look at. The first one being the Slwave EMI scanner and EMI workflow. That goes through a check of EMI rules, and then we're going to show a few examples of induced voltage, resonant modes, near field analysis, and far field analysis simulations. And then finally, we're going to take a look at the EMC test environment that is housed within HFSS and the Ansys electronics desktop, particularly around radiated emissions, conducted emissions, and radiated immunity. So what is EMI? So EMI stands for electromagnetic interference, and it's the undesired electromagnetic waves that can negatively impact a device's performance or cause harm to a nearby individual. And if you look at the picture on the right, EMI can be generated from current and voltage fluctuations present on a PCB or cables associated with the device. So what are some sources of EMI that would be present on a PCB? That would be your switch mode power supplies like a buck or boost converter, as well as high speed traces like DDR memory, Ethernet, PCIe, anything that's switching at a high speed or is pushing a considerable amount of current quickly. And using that picture as a reference, the EMI can be radiated or conducted. So some EMI will generate and radiate off the cables, and some will actually travel along the cables as well. So that's our radiated and conducted emissions. Things that are going to cause radiated emissions on your board are typically going to be traces that are often routed on external layers, as well as large planes on the PCB. And things that will propagate conducted emissions is typically usually exclusively on wires or cabling. And then EMC, electromagnetic compatibility, is the testing that's required for all electronic devices to be produced. And this is typically governed by either a national or global regulatory body. So I'm sure a lot of you are familiar with FCC, or in Europe we have RED, and then there's also ISO and CISPR standards as well. So we kind of covered what EMI is in a general sense, but why should we be concerned with it? So the first and foremost is we want to prevent harm to and from other devices in the same proximity. And this, a good example of this would be, say, take a hospital, for example. So you are on a wing of a hospital and you have a piece of medical equipment that is fundamental to the supporting life of a patient. And then on the floor above, you have some construction going on and they're using some power tools. If those power tools, as I mentioned before, fluctuations in current and voltage, those are going to induce some sort of emission. And in that example, it's going to be a conducted emission, and that can couple back down onto the power lines. And if EMC and EMI mitigation hasn't been taken into account, that energy could couple back onto the power line and into that medical device, causing an operational disruption, which would be very problematic. It could be disastrous. And so, that's an extreme case, but in the general world, day to day, if a device is emitting too much EMI, it can cause operational disruptions or even component failure or lifespan reduction on other equipment that is nearby. It can also degrade its own performance. And so if you have any sort of radio on your design that has a desired sensitivity to operate ideally, other components and circuits on your design could be self-quieting it and elevating the noise floor to a level that may not be in compliance with a cellular carrier's requirements. It could also impact the general signal integrity of your device. So that would be an instance of, coupled crosstalk or anything that would reduce the accuracy of some of those high-speed lines when in the presence of EMI that's generated from other parts on your board. And then also it needs to take into account harm to individuals. And that's typically caused by RF energy heating and heating the tissue. So these are all things that we need to keep in mind and why we should be concerned with EMI. So what can we do to mitigate it? So the typical process for mitigating EMI is revising the circuit schematic and revising the PCB layout. And this comes in a few different ways. The first and foremost is adding filtering components, so series ferrites off of power supplies or decoupling capacitors on power rails or on any signal traces that have a lot of energy flowing through them. You could add surface mount shielding, or you could add additional PCB layers to improve the signal shielding. By adding additional PCB layers, it allows you to move external traces that are routed on the tops and bottom onto internal layers and avoid them from radiating off the surface of the board. Oftentimes, these EMI problems present themselves when you're actually at the lab. You're finding out about this. And at the lab, there are little magnetic components called ferrite clamps that you could clamp on an existing external power cable or any other cable that's associated that plugs into your device, say an Ethernet cable or a USB cable, things along that nature. And sometimes the quick fix ferrite will solve the problem. But if you have a design and marketing team that has a vision for the product and the incorporation of a ferrite is unsightly, sometimes that's not an option. Additionally, maybe you have a device that has a very high product volume and the increase in your bill of materials to include that external ferrite clamp will impact your bottom line. Similarly, EMI absorber is another option that's quite expensive and is used often as a last resort when you're mitigating often cellular or any sort of radio desense issues. And so typically that's avoided for regular EMC compliance, but it's another quick fix, cost prohibitive option. The ideal option is making sure that all of these items have been addressed prior to the fabrication of the PCB, and that's where simulation can be your friend. And so simulation can help identify the potential problems of EMI before you fabricate the PCB. And you can also mitigate those problems prior to fabrication, and you can evaluate how effective those potential mitigation strategies will work. So here is the traditional EMC design workflow that has been, typically in place for decades now. You'll start with your circuit layout design. You'll do some internal PCB reviews that are based off of, best practices that your team or tribal knowledge is aware of. You'll fabricate your PCB. You'll get those back. You'll perform your general device bring-up testing, integrating it into its enclosure, any additional peripherals, and then you'll send that off to the lab for what's called an EMC spot check. Now, the spot check is important because if you just take your device that you've freshly created straight into the lab with the intention of completing a full regulatory certification before you know how your device performs for EMC, you could very easily get burned on that process. So say you're taking your EMC tests, everything's passing, going fine, and then you get to a radiated emissions test case and you fail. If this is your official test, all of the previous data has become invalid because now the change that's required to pass radiated emissions is no longer representative of the device that had passed the previous tests. So I always suggest product development companies and designers to incorporate an EMC spot check during the design phase to first identify all the issues so that you can make the relevant changes before going into a full compliance test. If it passes, you can go on to full regulatory certifications. That's great. If it doesn't, the typical design workflow is going back to the layout, refabricating, bringing it up, going back for spot checking, and repeating that. I read a statement from Intertech. They're one of the leading EMC test labs, and they said that anywhere from 50% to 90% of all new product designs will fail their EMC testing from their first iteration of their design. And this can become very expensive very quickly when you're looking at PCB fabrications in the thousands of dollars, having to get back scheduled with the test lab for additional testing, and it can start to jeopardize your product's launch time. So the goal is to, maybe not pass the first time. The end goal ultimately is to pass the first time, but sometimes there's always something that you may not catch. The goal is to make the failures as minimal as possible, if at all, so that you have a very clear, short list of things that you need to fix for that second revision so that you can stay on time. But from a design perspective and developing a timeline, it's always wise to at least incorporate a second spin in case you need it. So this brings us into how the Ansys EMI scanner workflow can help us with this process. So the goal from the previous slide is to minimize the amount of changes that are required in a revised board and minimize the amount of EMI that could potentially show up when we take it to the lab for evaluation. And so the workflow for the EMI scanner goes as follows. You will open the Ansys Slwave tool. This is the Ansys signal integrity tool. It is a 2 and 2.5D solver. It's typically known for developing eye diagrams, crosstalk, analyzing any general signal integrity and power integrity on your design. But it also has a tool that's called the EMI scanner. And that EMI scanner acts as a design check for EMI. So the first step is you import in your ECAD design. All of the major players in ECAD can import natively into Slwave via OBD++. So that brings in all your traces, your vias, your components, everything connected together. The next thing that you will do is you will select your rules for EMI. So this is similarly to a design rule checker for ECAD, but it's specifically for EMI and signal integrity. You will then, using those rules, identify the nets that you feel have the most potential for EMI problems. And this comes from an intimate knowledge of your design and is dependent on a design-to-design basis. So you as the engineer or designer and layout team have control over what portions of the design you want to analyze to effectively improve the design workflow as you're laying out the PCB. You will run the EMI scanner, and that will output the evaluation of the design and show you all of the flagged issues and rate them on a degree of severity. And then if you want to take it the next step further, you could actually perform full wave EMI analysis on the failures to get better insight as to what frequencies and regions and the fundamental interaction of how that EMI failure is being generated. And that's done through a resonant mode, an induced voltage, a near field, or a far field. So the first thing that we want to dive into is the actual EMI scanner rule selection. So what you do here is you have a set of rules that you can choose that the EMI scanner will check the entire PCB and components against to identify any EMI failures. So this is intended to be used in conjunction with a traditional layout review. So if you have EMC layout knowledge and you have best practices that you like to follow, you know, it can happen where if you're looking at the board manually, there's things that are going to slip through the cracks. You know, this is going to give you a complete list of every single violation that is occurring on your board based off of the best practices that you could set, as well as if you don't have a lot of knowledge in this area yet, there are preloaded rule sets that you can use that are frequency specific, that are that can be used so that you could have no EMC knowledge and you could load this tool and it will help point you in the direction of some issues. And what's nice with that is if you do have a set of independent rules that your group typically will follow for EMC, you can save and load those rule files into new EMI scanner designs to save time. So you only have to set up this rule setup once, and then it's a file that you can import in, and then all of those changes will be brought in natively. And it's important to choose your nets wisely. So you could have this run against every single net in your PCB, but it's going to take a lot of time to sift through a lot of non-issues. And so the typical recommendation that I would give is to know which nets are critical. So those will typically be, you know, your power nets, your high-speed nets, anything that's switching. And you can assign those nets as critical. And by showing the net choice as critical nets only, you can limit your EMI scanner to look at only the things that are important. And so why does this matter? Why wouldn't I want to just have everything on my plate? So take, for example, you get if you had all the nets, some of them, it doesn't matter if that violation occurs. Some of them are static nets that aren't doing anything and don't have any likelihood of causing EMI. And if you go trying to fix some of those suggestions, you might be taking up valuable real estate in your PCB layout that could be dedicated towards fixing some of the more important, pertinent, critical nets. And so it's a little bit of a give and take, but this is something to keep in mind when you're assigning rules. And so now, once the rules have been done, you run the EMI scanner. It's a very quick, you know, minutes output, very fast. And what you get here is two representations of what's going on. So on the left here below is the list of all of your EMI scan violations that are organized by the violation category. And then you'll see the red to green severity bar. It will assign each net a severity level based off of the weighting that you've assigned it in the rules, as well as the severity of how bad it is outside of the spec that you have set for that rule. So right now we are looking at a rule that is a signal trace crossing over varying reference planes. So right now we have an internal trace that's routing that references a power plane layer, and in that red box, it's crossing over a few different planes. And so when you click on one of those violations, it will tell you what rule it's violated, how severe it's violated, the nets that are involved, as well as the layers and XY axis location information. And then it will automatically populate that red square on your design and show you directly where your issue is coming from. And so beyond this, now you kind of see, okay, let's take a look and see what can be done with some of these major violations. So this one is a critical net crossing over the reference plane. It's listed as rather severe. It's got a red, orange. So that's something we'd want to take a look at and see what's going on. Which brings us to the induced voltages. So now we set up an induced voltage simulation, which is effectively sending a plane wave from all angles, so all sides of the PCB, up, down, left, right, front, back. And what it's looking at is the induced voltages on that specific trace that we have there, that net. And what it outputs is a voltage fluctuation over frequency over all of the plane wave orientation. So that's where all of the traces here you see. And so this data is generated through the Ansys Electronics desktop. It is pushed from Slwave into the Electronics desktop. And what's useful with this data is it tells you a couple things. One, it tells you what frequencies that specific trace is susceptible to from outside EMI. So if you had a device in proximity that had EMI at 580 megahertz or 320 megahertz, those are some of the peaks there that you see. That energy will couple onto this trace rather easily. And inversely to that, energy traveling from this design will also radiate just as easily at those frequencies. And so this tells us, we know that this is an EMI violation, but what frequency and how bad could this actually show up in an EMC plot? So then you take the induced voltage values. So you make a mental note what frequencies those peaks are at. And then we go into what's called the resonant mode analysis. And what the resonant mode analysis does is you specify a span of frequency range to analyze that net for resonant modes. And you will then get a list of all of the resonant modes that have been calculated, and then you narrow into the one that's the closest in frequency to what you are seeing in your induced voltage simulation. And as you can see here, when you animate it, you can see right at that plane crossing, we have a resonance that is causing EMI. And the resonant mode is looking at the interaction between planes on either adjacent layers or layers that are coupled with one another. So this is typically something that you'll see on the top layers or the layers right below, or any layer where there's a void in copper that can couple to ones down further. And so using these two tools together, this is a very quick pinpoint as to where you have EMI and what parts of the geometry on your layout you might need to consider fixing. So here it looks like the region that we see with the greatest color change here. So this graph is showing it at positive to negative voltage swing. So it's sweeping over the voltage or over the phase. And so you can see the resonance here. And so this is telling me that I need to make some improvements in my layout to get this improved. And you can do some layout changes within Slwave. If there's any, say if I wanted to move this trace to a different layer to reference a different layer, say reference ground or instead of power, I could do that as long as I have space within my layout to do it. If it's going to start violating other traces or planes, it's better to make the change within the ECAD tool and then re-export your OBD++ and re-import it into the Slwave and rerun this analysis. And so you can run this net by net for all of the nets that the EMI scanner has identified, write them all down, make a list of all the things you want to fix, go make the fixes, bring it back in, and rerun the induced voltage and resonant mode analysis. And then you can see how your changes have improved the robustness of the EMI mitigation on your board. And then the next step further that you can take this, and so what I suggest is you stay primarily in the induced voltage and resonant mode region. It's the fastest. This thing simulates in minutes. You can iterate your design relatively quickly, but if you want to also go into a deeper dive into what you would like to see from an EMI perspective, say if you really want to know how something is going to radiate on your board, say if you have like an oscillator or a high-speed data line or a power supply, something that you know is noisy and you really want to get some field data out of it beyond resonance, you can take it the next step further and perform the near field and far field analysis. And this uses the electronics desktop and HFSS to couple with Slwave. So the first thing that happens is you will assign what net you are interested in. In this example, it's a SPI clock line that operates at 150 megahertz. And you will generate an S parameter from within Slwave. And then in Electronics Desktop, you will create a circuit model. And what the circuit model is showing is it's showing the ports and the source and termination ports of the oscillator. And then in the center, we have imported in the Slwave S parameter extraction. So it's an Slwave design. And on these circuit models, these are just IBIS models. And what it's simulating is it's simulating a bit pattern, or effectively the clock pattern that is being driven by this oscillator. So the frequency, jitter, all of the parameters that are associated with the signal. You'll solve it within the circuit simulation, and then you'll push that excitation back into Slwave. And then using the S parameter extraction and the circuit data, Slwave can then compute the near field and tell you where the source of radiation in the near field is predominantly residing. And it can also calculate that in the far field as well, and that data is going to be represented through HFSS in the Electronics Desktop. And you can effectively get an idea of how high or how near the compliance level you could be hitting based off of what your far field data is showing for a specific frequency. So here we have a peak right around 450 megahertz. So that looks to be close to a third harmonic of that 150 megahertz. So let's take a deeper dive into how this is all done. So the first step in this, it starts with jumping off from the resonant mode. So the resonant mode is your jumping off point if you want to go into near field and far field analysis. So now I'm looking at that SPI line, and I ran my my mode analysis. I found a frequency mode 13, which is at 429 megahertz. So that's pretty close to 150. It's the closest one for the mode. I'm sure if we had a mode calculated right at 450, this would be even stronger. But you can see we have a very strong resonance on this power plane caused by that oscillator. So we're looking at the power plane referenced to ground. So the power plane is what is resonating and potentially radiating EMI. And so once we know that this is a spot that we're interested in looking at, we extract the S parameter data, we push the circuit model, and then we run the near field analysis in Slwave. And this is kind of what the near field analysis results plots will show you. You can choose how many frequencies you want to evaluate the near field for. You'll get an overview on the maximum E field. You could animate this if you wanted. And you can see that I have the EMI scanner down here, and I've clicked on my violation. So what we're looking at here is the violation that flagged this area in the first place was that there wasn't enough decoupling capacitors in this region. And so this is, it's kind of cool to see that the EMI scanner does accurately predict the location of the highest field strength. So when I clicked on this capacitor density, it gave me a flag that this is a region that has low density for decoupling capacitors, and then it's proven by the near field analysis that we have a hot spot. And this is also useful, like I said, for self-quieting problems. So if you have a device that's passing EMC or FCC or any of the regulatory bodies, but you have a radio on board that you feel is either not having good enough receiver performance, or if you've actually taken it to a compliance, cellular compliance lab, and they've said that you fail, you don't meet their sensitivity requirements, you could bring your board in and help pinpoint the actual sources of the issue. And here we have the far field. So this is just showing a magnitude representation of the far field for over frequency. And this is solved within Slwave and is pushed out to the Electronics Desktop. And like I said before, it does use IBIS models for the circuit. You could also use SPICE models or just standard circuit blocks that are within the tool. And this kind of helps round out the response that you would be expecting to see in this analysis. And so what's really powerful with this tool is that you can try out the inclusion of components without having to change your ECAD. So I mentioned before that there is the ability to adjust your traces and your layouts to an extent, as long as it's not interfering with anything within the already laid out part of the board. Changing major things in the layout is better spent in your actual native ECAD environment. But what Slwave does very well is the incorporation of components on the fly to try out mitigation methods right then and there. So the example that I have here right now, on the left, that is the frequency swept near field analysis that I showed you prior on that clock line. So that's this data right here. So right now you see it's the peak value at 450, but we are sweeping from 400 to 500 megahertz. And that's what this is showing here. I can very simply, in that region, I clicked on a spot that had the power plane present. I drew a little port that I said I want to create a decoupling capacitor for. I assigned that to 10 microfarads, and I reran my decoupling analysis. And what you can see is that the violation has been mitigated considerably. There's still a little bit over here, so maybe this is worth adding another decoupling component right here. But ultimately, you're getting near real-time feedback that gives you the confidence that your mitigation methods are going to work. So you learn what's your problem, you can fix it, and this is all being done before you've actually fabricated your design. And so if you go through all of your critical nets, all of your power planes, all of your ground planes, you can identify all the potential sources of EMI and make a significant number of component level improvements before you actually fabricate it. And that's the end goal, is to get this catch as many of these things before you actually have to make the board and get it spot checked to see if it will pass. And that brings us into the next phase. So what I've been talking about has been predominantly hosted in Slwave and is the most effective means of evaluating for EMI, because it pinpoints all of the different sources, potential causes, and means of radiation. But some individuals, some companies, and product developers want to get an insight into how the device will actually perform when it's in a simulated test environment. And so this is where HFSS starts to shine. And so using HFSS, you can bring in your design integrated with all its cables, power supplies, signal sources, everything that's, you effectively make your device operating as closely as real life that it would in the test lab as possible. And that's done through the circuit tool that I'm showing right here. And in the center of this circuit model is the physical RF design that you see in the lower left here. And so you assign all of your signals accordingly. And some of the things that you have control over are the device under test, the cable harnesses, the anechoic chamber's presence, and then of course the test antenna. And the output is what you typically will see from, or what you typically expect to see from a certification lab. A log plot that is showing all of your EMC potential issues and just the general radiated performance of the device. Furthermore, you can plot fields. That's what this animation is showing right here, a phase-dependent field plot of where the energy is being radiated and how it is propagating through free space to the test antenna. And some of these setups come as standard examples within the HFSS tool. And you can use those as a starting point and then customize them accordingly for the compliance standard that you are trying to test against. And so this is particularly useful, but it does come at a cost. The cost primarily being simulation complexity and time. So if we were to compare the simulations on the Slwave EMI tools, even the far field and near field data that I showed, this is still orders of magnitude more time and computationally exhaustive because we are calculating the full 3D wave in this scenario. This becomes increasingly prohibitive as you go higher in frequency. So when you start going at above 1 gigahertz, this is effectively solving the fields throughout the entire 3-meter space for this example. So you can imagine at the wavelength of for 2 gigahertz, that's quite a few unit cells that is required to do the full solve. And in doing so, the simulation time goes up considerably. And the other cost at this is it gives you a very close representation of what you'd actually get at the lab. However, it doesn't necessarily give you a whole lot of insight as to why the results are showing that. You're going to get those from the EMI scanner much more clearly and quickly than you would with the radiated emissions through HFSS. That's not to say that this doesn't have its place. There's certainly instances where if a company if they had a lot of time, but for internal reasons, they absolutely needed to have, no more than one board spin, and they want to know for sure that they will pass, or if they have an external customer that is requiring assertions that their setup will and their device and products will work accordingly and pass regulatory testing. This is a way to get that confidence. But from a general design workflow method, I would suggest that you stay primarily within the EMI Slwave tool. That's just because the amount of value and answers and quickness, it's much more intuitive to your workflow to use the EMI scanner workflow during your design phase than this. This is sort of at the end. You could do this if you wanted to check, but like I mentioned, sometimes if you don't have a computationally powerful machine, these simulations can take a considerable amount of time. So it's something to consider, but it is a neat feature that is existing within the tool set. And so aside with the radiated emissions, you can also do the same thing for conducted emissions. So here you bring in that same device under test, the cable harnesses. The circuit model has the line impedance stabilization network, or LISN, the same thing that you'll find at the compliance lab to decouple from the noise from the main power supply. It has the power source, and you get the same as you typically see emissions plots for your conducted emissions. So again, you design for EMC using the EMI workflow, and then using the EMC test environments within HFSS, you are able to very clearly see what you can get. But I would say that for the majority of designers, this isn't something that you would necessarily need to use, but it is something that is available and something that you would have access to with access to the EMI scanner as well. So it's just an additional layer of confidence that can be instilled upon your design, and then you can get your actual data that will match very, very closely to the actual test data. And the only variances that you'll typically see between measured data from the lab and simulated data from the environment is the degree of excitations that you have on your board. So the simulation will only be as good as the number of signals that you excite. And so if you have a lot of peripherals off the board, if you don't include those, well, it can't simulate the radiated or conducted effects of those devices. If you don't assign circuit IVUS models to the ports of the memory or any high-speed traces, the same thing occurs. So the goal with using the EMC test environment within HFSS is to ensure that you can assign as many signals as you possibly can, within reason, of course. And so that comes back to making sure you're choosing your signals correctly. And that always comes with just the intimate knowledge within the design that the designers and engineers have. And then the third example that can be seen within the HFSS tool set is as well radiated immunity. So this is simulating a automobile, looking at susceptibility to radiated EMI, and the field plots that are relevant to that. All important things to see, to understand, and it helps also kind of visualize where the energy is actually radiating off your board and the method of how it's radiating. So that's the other benefit from this EMC test environment. It's to help the engineers visualize where the energy is truly coming off of your device or your system, where the energy is coupling onto your device or your system, and using the two together gives you the ultimate result. But for just very quick incorporation, the EMI scanner is definitely the way to go. But some people care, and this is what's really powerful with the tool of HFSS and the electronics desktop. And as you can see here, this is an example from an IEEE paper. They simulated the radiated immunity, that's the plot here on the bottom, and then they also took physical lab measurements, and they line up very, very closely to one another. So you will get a very high degree of confidence, accurate answer, so long as you take the time to make sure that your model is well refined and optimized for the test setup that you're looking at. And so here are just some of the regulatory standards that can be leveraged within this HFSS EMC environment. Your standard CISPR 22, CISPR 25 for automotive, and all your IEC and ISO standards. A couple of things that I didn't show here, but that are examples within HFSS that you could just open up an example and use that as a starting point is for electrostatic discharge, as well as voltage transients or electromagnetic pulses. So those are other things that you could simulate and evaluate within the HFSS tool so that you at least have an idea of how well it will perform prior to fabrication of your circuit boards. So in summary, EMC design is important for all electronic devices, and using the Ansys electromagnetic tools will reduce the number of PCB iterations that you'll have to go through and the potential schedule risk. The EMI scanner is a designer's best friend during the development because it ensures that you have a robust design that is protected against self-quieting, protected against incoming EMI, and it's mitigating and ensuring very minimal EMI is actually coming off of your device. If you want to take it into the full simulated test setup, you can bring that into the HFSS EMC test environment for a very accurate estimate to the outcome of regulatory testing prior to even fabricating your board. And it's important to mention that to access the EMI scanner and the EMC test environment, you will have to leverage an Ansys Electromagnetics Enterprise license. And so if you have any questions about how to access that, or if there's any interest in some of these tools, but you either don't know where to start or want to have some outside help, the team here at Ransom would be more than happy to assist you in any way with that effort. So with that being said, I wanted to thank you all for attending this webinar today, and I'm going to open up the floor for questions now.
Great. I do have a couple of questions, but if you find that you've got a question, you can just type it in. Right-hand side, there is a questions box for you. So the first question I've got, how is the incorporation of shields evaluated within the EMI workflow?
That's a great question. So as I mentioned previously, shields is one of the most common methods to fix a PCB EMI failure. And oftentimes it's become a EMC best practice to incorporate shields, or at least have a provision for a shield over areas that from past knowledge or just general EMC knowledge could have a cause of radiation. And so the way that Slwave and HFSS will do that is you'll first generate the near field analysis within Slwave, and then you can export that near field data into HFSS. And then within HFSS, you then draw or bring in your 3D model of your shield onto your PCB. And using the near field data from Slwave, you don't need to recompute the near fields in HFSS. You are just using the fields and then allowing those fields to propagate now in the with the presence of the shield. And the HFSS will then compute using the near field as sort of like a seed field, seeding the data. It will then show you the adjusted near field with the shield present. And so it's an additional step, but it's something that can be incorporated within the linkages of those two tools.
Okay. Is there a preference for import ODB++ or IPC 2581? And is there any support for Gerber import?
So all of those can be imported. The preferred import is most certainly OBD++. And the reason being is that it's all natively packaged together. With Gerbers, the challenge is that you don't get the net linkages very well because it's coming in as layers, and the OBD++ will typically import much more nicely. And fortunately, if you have any of the main ECAD out there, Mentor Graphics, Altium, there are Ansys videos online that show you and walk you through all the steps on how to generate the OBD++ files, and as well as the component files, so that when you import it in, it all just comes in and is ready to go.
Okay. Where should I focus the majority of my simulation workflow, like the EMC environment or the full field EMC solver?
Yeah, so like I was mentioning previously, the EMI, the full EMC simulation environment is sort of a last check if you want to do it at all. The majority of your EMC during the design phase should be primarily housed within the EMI scanner and the EMI workflow. The value versus time output is much greater in the EMI workflow within Slwave, so that you could be running multiple simulations throughout the day as you're making changes. And because the importing of the CAD files or even changing components on the fly, like that decoupling capacitor example that I shared, all those things can be done within Slwave, and the simulation is in the matter of minutes, versus in HFSS, the simulation could be hours or even days. So the primary, I think for the majority of the people listening on this webinar, I think they would most benefit from the EMI scanner and EMI workflow within Slwave. But if they did have any questions about either of the tools, we're more than happy to help answer those.